Okay, here's another related rates problem. So take some time to read this. There's this guy pulling this plank up this wall. Now it's saying that, well, here, not sure I like that diagram. I'm going to redraw it as you're reading this. So I'm going to blow this part up. This forms a triangle, and so let's read it again. The worker's pulling the rope up at a rate of 15.15 meters per second. So that means this point is changing, which means this whole side is changing. So this side right here is getting bigger at this rate. Then this also forces this side, if you're pulling this plank up, to get smaller at a certain rate. So how fast is the end of the plank sliding along the ground? So that's this part, and it's asking how fast is this sliding. So that's just kind of translating the question. Now we're going to label our diagram and figure out where all the variables are. So here, variable is a key word. We have this side I'm going to call y, simply because it's up and down. It's like the y-axis. This side I'm going to call x. So we have to find a relationship between these sides. And since this is a right triangle, that's going to be Pythagorean theorem. One thing it's useful to take into account, though, is we're going to have to bring this z side in, the hypotenuse, but it's not a variable. It's always 5. X is a variable because it's changing, it's getting smaller. Y is a variable because it's changing, it's getting larger. But z is not a variable. So don't even label it with a variable, because when you take the derivative, it will be 0 because it's not changing. So that's one big thing on this problem. So let's start identifying everything. This is going to be dy dt because it's how y is changing. And they tell us it's changing at 0.15 meters per second. That's a rate, meters per second. So it is dy dt. Okay, so how fast is the end of the plank sliding? So that's the question, is how quickly is this sliding, which is dx dt, because it's the rate at which this side x is changing. When it is 2.5 meters from the wall of the building. So we're looking for the rate at which this is changing exactly when x equals 2.5. Now 2.5 is not a constant, it's changing. It's getting smaller, you can see that. So we're just going to say x equals 2.5 here. But we're not going to do what we did over here and just ignore the variable because it is changing. So we're going to set up the equation, which would be x squared plus y squared equals 5 squared. See how I don't call that z? Because it's not changing. I'm going to create a related rates equation by differentiating with respect to t. So 2x dx dt plus 2y dy dt equals 0. I'm going to divide by 2 because I can. check out all of my knowns and unknowns. We know that dy dt is 0.25, 0.15. We know that x is 2.5. We know we're solving for dx dt. We don't know y. So first we have to get y. But we need to find y exactly at this point when x is 2.5. So we can just figure out what it is based off that equation. So grab my calculator. We have 25 minus 2.5 squared. And we'll take the square root of that answer. And I'm getting approximately 4.33013. I'll keep it as many decimals as I can, just so my final answer is accurate. So now I can solve. So now it's time to plug everything in. So x we said was 2.5. dx dt is what we're trying to solve for. Y we calculated to be 4.3301. And I'm going to use the number I got in my calculator, which is longer than this, just so I'm as accurate as possible. Dy dt is 0.15. And that equals 0. So solve for dx dt. That will be negative 4.33, and that's whatever I got in my calculator I'm going to throw in there, times 0.15 over 2.5. So grab the calculator. And I got negative 0.2598. So I'm just going to leave it there. And that would be dx dt, so it's meters per second. And it is negative, which makes sense because x is getting smaller. So there you go.